So some of this will be review. So a random variable is what? It's a function from the sample space of an experiment into the set of real numbers. So if the experiment is to select 10 people, then my sample would be the people selected, and a random variable x could be the weight of a selected person. So if my people are x1, x2, and we'll go through x10, then x of x5 might be 150 pounds. And x the random variable of the person, x say 9, could be 120 pounds. X is a function. It maps, this would be an element of the sample space, into the real numbers. So that's all a random variable is. But it's a very useful concept. Now, on a given experiment, you can have multiple random variables. So for the same 10 people, y could equal the height. And then we could talk about y of, I'm going to keep the same notation here for people. I could talk about y of x4 would be, maybe that person was 5 foot 7 inches. And y of the second person, we call that x2, might be 6 foot 2 inches. So you get the idea there. Now if I take a random variable with its values, the values it can take, and the probabilities that it takes those values, then I've got a probability distribution. Let me see if I can spell distribution a little better. A probability distribution. And I think we could come up with an example of that. We need an experiment. Let's toss 3 coins, and let's let x equal the number of heads. Then x takes, we often say x takes the values, but really this is the range using functional notation. It's the range of the random variable x, and it would take the values 0, 1, 2, 3. So the values that x can assume would be 0, 1, 2, 3. If I toss the coin and get 2 heads, then on that outcome x maps into 2. All right, now it is often convenient to do a probability distribution in the discrete case as a little T diagram, 0, 1, 2, 3 in this case. And then over here, we'll put the probability that x is equal to lowercase x. These are the lowercase x values. They're the values that the big X takes. And maybe it's an exercise to see where these numbers came from, but it would be 1/8, 3/8, 3/8, and 1/8. And what does that tell me? That tells me that the probability that x is equal to 2 is equal to, let's look it up, is equal to 3/8. So another thing that tells me is that 3/8 of the time, if I repeat this experiment a large number of times, about 3/8 of the time, I'm going to get exactly 2 heads. All right, so this is a probability distribution. Now, very, very often, and in fact, I might even say usually, we get these probabilities. These came from just considering flipping coins and writing down the sample space and seeing how many ways you can get no heads or one head. But very often we have a probability function. And in the discrete case, this is very often called a probability mass function. Probability mass. Probability mass function. In the continuous case, it would be called a probability density function. And the probability density function we're going to save until the next lecture. We're going to deal today with the probability mass function. So let's go scrolling here a bit and hope for the very best. So we'll stick with our 3 coins. Now we could let f of x equal 3 choose x. So we're using some of that review stuff. 1/2 to the power 3. And this would be a probability mass function for number of heads, 3 coin, number of heads in a 3 coin toss. Because it's a probability mass function for this experiment because it gives me the probabilities. The probability that x is equal to, just pick a number, let's just pick 2. Now let's use the probability mass function and see if this thing actually works. Well, this would be 3 choose 2, 1/2 cubed. 3 choose 2 would be 3, and 1/2 cubed would be 1/8, so this would be 3/8. Now we can verify and make sure that it agrees with what we got earlier, and you know, it does. And that would be true for all the values that this random variable takes. This is a probability mass function. Now, in order to be a probability mass function, there are some requirements. So a function g of x can be a probability mass function. This would be a discrete case now. If 1 g of x is greater than or equal to 0 for all x in the range of the random variable, and 2 sigma g of x is equal to 1 when I add over all the x's again in the range of the random variable x. Now we can see that that happens here in the case of this f of x for tossing the three coins. These are the probabilities that this function would give me. If I add them up, I've got 1/8, 4/8, 7/8, 8/8, and 8/8 is 1. And I see that all of these values are positive. So 1 and 2 hold, and this f can be a probability mass function. It is a probability mass function. Now, besides the probability mass function, we have a probability distribution function, sometimes called the cumulative distribution function, and it is designated capital F of x, and it's equal to sigma. Now this is in the discrete case. We're just dealing with the discrete today. For t less than or equal to x f of t. So for the tossing the three coins, my distribution function evaluated at 2 would just be f of 0 plus f of 1 plus f of 2. And this would be, I'm going from memory now, but as memory serves me, I think this was 1/8 plus 3/8 plus 3/8 would be 7/8. And that would be the value of f of 2. That would also, of course, be the probability that the random variable is less than or equal to the value 2. Now we can graph these things, and sometimes we get a lot of insight by looking at graphs. So let's try a probability histogram. We're going to stick with the three coins, and I can see I'm going to have to get a new piece of paper here in a second. So sticking with our three coins, a probability histogram, this is a sketch, excuse these lines not being as straight as I'd like them. 0, 1, 2, 3. And let's get some scale on this vertical axis. Now this would be probability over here. So this would be probability, and this would be number of heads. All right, and so this goes up to, why don't we just make this 3/8 here, and then this can be 2/8, and this could be 1/8. So if we're going to do a histogram for the probability mass function f of x, it would look like this. So these bars are of width 1, and the height is the probability that the value occurs. Now, that is just traditional. We always, or often anyway, draw those probability mass function histograms that way. But there's argument for saying that this would be more appropriate. See, I guess after 0 comes 1, doesn't it? 0, 1, 2, 3. It would be more appropriate to draw the probability mass function like this. These are straight lines. You should be drawing a map because these look more like rivers on a map than they do straight lines. These two would be exactly the same height, and these two would be the same height. Now, this is a technical argument here, but why would people think this graph was preferable to this one? Well, because this one gives the impression that the probability of the random variable being equal to 2 is somehow spread out over this area of the horizontal axis between, this would be 3/2 and this would be 2.5 or 5/2. But in fact, that probability is not spread out between those two dots. The probability resides right here. And so the line graph is actually a better representation. We're going to pause here for just a second because I'm out of paper, and so we'll get some more paper. So you hold on. You won't even know that I'm gone. All right, I think I'm back. I hope I'm back. Another notion that we want to illustrate today is what would the graph of the distribution function look like, f of x. Now, let's stick with our 3 coins. It's a good example. And let's refresh our memory. We've got x, the random variable, and it takes 0, 1, 2, 3. And the probabilities, I could write these probabilities as the probability that x is equal to the lowercase x, these being the lowercase x's, or we could write it using the probability mass function as f of x, and I choose right now to write that as f of x. And we know a function for f of x, an algebraic relationship, but I also just remember that those values work out to be exactly these values. Now in this T diagram, that much that I have right now, that much is a probability distribution. And a thing to know about a probability distribution, if you add these values, they always have to add to 1. And if they don't add to 1, you've made a big mistake somewhere. Let's see what we've got. 1 and 3 is 4, and 3 is 7, and 1 is 8. 8 over 8, and that equals 1. Well, it had to. And now let's get the cumulative distribution. So this would mean the probability, what I'm going to write right here is the probability that the random variable is less than or equal to the lowercase x. So what's the probability that the random variable is less than or equal to 0? Well, less than or equal to 0 just means, because it's discrete, just means equal to 0, so that would be 1/8. What I want to write here is the probability that x is less than or equal to 1. Now, less than or equal to 1, because it's discrete, means it would have to be equal to 0 or equal to 1. And the or would be disjoint. Remember from a few days ago, we name those things. That would be 1/8 plus 3/8 because these are disjoint events. So that would be 4/8, which I could have written as 1/2, but it's convenient to keep these all as 8s, I think. What goes here would be capital F of 2, which would be f of 0 plus f of 1 plus f of 2. So this would be 7/8. And finally, I'd have to add in this last 8, and so that would be 8/8. Now, when we're doing the cumulative function, if we're doing it in a T diagram like this last value here always has to be 1, because this is the probability that x is less than or equal to the largest value it can take. And that probability would have to be 1. And we can draw a graph of this as well. And we'd let that be 0, 1, 2, 3, and maybe just make this a little bit taller. And we put 1 up here, and we put 1/2 in here, and so this would be 3/4, and this would be 1/4. So that's enough scale for a sketch anyway. So the sketch would go like this. I'm going to change color. The probability of being less than 0 is 0. So my cumulative distribution would be 0 until I got up to 0. Now at 0, it immediately jumps to 1/8, and that would be 1/2 of a fourth, and so it would jump to here. But that probability is going to stay 1/8 until I get over to 1. And when I get to 1, it's going to jump immediately to 4/8, and 4/8 is 1/2, and so it's going to jump up to here. And like that. And then at 2, it's going to jump to 7/8. So 7/8 would be way up here somewhere until I get to 3, and at 3, we're going to jump to 1. Now, I'm going to color is such a beautiful thing. I'm going to fill in these verticals because I want you to observe something here, and it's a little easier if we've got these vertical lines. This vertical line right here is the probability that x is equal to 2. That is, the distance or the length or the value of the length of that green line right here is the probability x is equal to 2. How did we get the cumulative from this value to this value? We added in the probability that x was equal to 2. It made a jump here, and the size of the jump is probability x is equal to 2. And by the same token, this is the probability that x is equal to 1. So a knowledge of that may occasionally be useful. All right, what to do? Well, I'm going to go ahead and make an assignment. Assign page 80, problems 3.1, 3.3, 3.6, 3.9, and 3.14. Those won't all be on page 80, but this page 80 and following pages. And now let's do some example problems. Out of this set, let's work problem 3.5. And you'll want to maybe look at problem 3.5 in your textbook. It's on page 80. But here's, in essence, what it says. It says, for what values of k can, I called it f again, f of x equal 1 minus k, k to the power x, x equal 0, 1, 2, and so forth, be a probability mass function, question mark. All right, observe that this random variable is discrete. Its independent variable can be 0 or 1 or 2, but it can't be 1.5 or 3.5. it's a discrete random variable, and this is the probability mass function for that discrete random variable. Note also that this is countably infinite, so these go on to infinity. It doesn't end at 2. That's what the dots mean. It goes on forever. So what does the question mean? What values of k can you put in here and keep f of x, a function that could serve as a probability mass function? Well, the answer is easier than maybe what it first sounded like, because a probability mass function has got to satisfy just 2 conditions. For all x, f of x has got to be greater than or equal to 0. That's condition 1. And condition 2 is the sigma over all the x values, f of x must equal 1. So now we can use some of the sense God gave us and see what these 2 conditions say about the k that's in this formula. Well, first of all, I notice that k must be greater than 0. Now, why is that? It's because if k is less than 0, for odd x, f of x would be less than 0. See, what do we got here? If k is any value less than 0, when I raise it to an odd power, then this term is going to be negative. And I guess if k is beyond -1, this is going to be positive, and we're going to get a negative number here, so we can't have that. And why did I say greater than 0? Why didn't I say greater than or equal to 0? If k is equal to 0, so this will be a note bono, k equals 0 implies that f of x is identically equal to 0, and therefore sigma f of x, that's the second condition, cannot be 1. So we don't know as much as we'd like to know, but we know something. Now we also must have sigma f of x being equal to 1. Let's see, I'm going to erase that little thing and just put a 1 here and say equal, and this would be x equal 0 to infinity. Now what is that? That would be sigma x equals 0 to infinity 1 minus k, k to the x. Now k is not a summand in here. K is constant. It's x that's the index. So this 1 minus k can come out. 1 minus k sigma x equals 0 to infinity k to the x, and that's a geometric series, an infinite series, and this converges to 1. Well, I've got this k subtracted from 1 out here in front. Now let's just talk about let's talk about the series. It converges to 1 over k, no, 1 minus k. I'm not pronouncing very well here. It converges, the series converges to 1 over 1 minus k if the absolute value of k is less than 1. And that would mean that, holy granola, that would mean -1 less than k less than 1, but we know that k has got to be greater than 0, so we conclude if 0 less than k less than 1, then f of x equal 1 minus k to the x can be a probability mass function. All right, so I would say that was fun. And maybe let's do one more. I've got several of these that I worked out, but we won't do all of them. Let's look at 310 as an example. And in 310, we've got a function f of x, that's an x, is equal to 2 choose x, 4 choose 3 minus x, over 6 choose 3. X equals 0, 1, 2. So, is this a probability mass function? And if so, graph f of x. Well, maybe the easiest way to see if this is a probability mass function, since it's discrete and is very small, would be to just start out with the random variable x, and let's see what values x can take. Well, it's given right here. X can be 0, or 1, or 2. Now, let's calculate f of x. Well, if x is 0, then go to our formula. 2 choose 0 is 1. This would be 4 choose 3 if x is 0. 4 choose 3 is 4. And 6 choose 3 is 20. So I get 4 over 20. If x is 1, I get 2 choose 1, that's 2. And 4 choose 3, that's 6. So 2 times 6 is 12, and this is constant, it's still going to be 20. So this would be a 12 over 20. And if x is 2, 2 choose 2 is 1, and this would be 3 minus 2, which would be 1. So 4 choose 1, 4 choose 1 is 4. So it's 1 times 4 over 20. 4 over 20. Now, at this point, we're going to check on ourselves, because if we have done this right, these will add up to 1. 4 and 12 is 16, and 4 is 20 over 20. So the sigma f of x is equal to 1. Good. You know, when that adds to 1, it doesn't mean that we've done it right. It's just that if it doesn't add to 1, it means we've done it wrong. Now, the directions for this problem said to graph the cumulative, that is, to graph the capital F of x function. So the values of the cap f would be 4 over 20, because the first value, cap f of 0, would be the probability of being less than or equal to 0. It's got to be 0 if it's less than or equal to 0. There's nothing else it can be. That's a 4 over 20. Cap f of 1 would be the probability that that x is less than or equal to 1. So that would be the sum of these two would be 16 over 20. And less than or equal to 2 would be the sum of all of these would be 20 over 20. Remember, another check if we've done this right, this must be 1. it is, and so we've probably done all that right. And it shouldn't take us too long now to draw cap fx. So why don't we make this 1 and make this 1/2. That would make this 3/4. These are just sketches now, so you could draw this with more precision. But this will be good enough for right now. So this would be 0 and 1 and 2. And we don't know what the random variable is, but this is the values of the random variable on that axis, and this is probability on that axis. So f of x, I'm going to change colors again. Before we get to 0, f of capital F, the big F of x, would be 0. The probability of being strictly less than 0 would be 0. It can't happen. And then 4/20 is 1/5, and so that's going to be about there. We're going to jump to 4/20, and then we're going to jump to 16/20, so that's a little more than 1/2, and so that's up about right here. And then at 2, we're going to jump 4/20 more, and we're going to be at 20/20. So we're going to look like that. Now remember, how high is this? Well, that's the jump at 2. So that's just the probability that x is equal to 2, which is lowercase f of 2. And this is long, but I've got a little bit of paper left, so let's take a shot at this. This is exercise 3:15. We'll just do one of these. Assume the random variable x takes x1, x2 through xn, and also assume, if you've got these values it takes, you can always arrange them in increasing order. So assume also that x1 is less than or equal to x2 is less than or equal to x3 less than or equal to xn, and then show part A, the probability that x is greater than xi, any of the i's that would fit between 1 and n, is equal to, well, let's evaluate it. I won't write down the answer and then show, we'll write it down as we go here. This is probability, so all the review that we've had and everything you learned in the elementary statistics course applies, and the law of complements tells me that the random variable x greater than xi would be the same as 1 minus the probability of the random variable x. Now the complement of less than xi would be less than or equal to xi, and this would be 1 minus x less than or equal to xi. That's just f of xi. And in fact, that's what problem A was about. I want to tell you one other thing. So I'm going to go ahead and do part B. Part B tells us to evaluate the probability that x is greater than or equal to xi. And the law of complements, again, tells me that that would be equal to 1 minus the probability that x is less than xi. See, the complement of greater than or equal to would be less than, but I don't really have a way to get the probability that x is less than xi, because this f function is less than or equal to xi. But we're dealing with a discrete random variable today. If xi is discrete, if you're not up to xi, you must be less than or equal to xi minus 1. So what I'm saying is, and you can think about this when I'm gone, this is the probability that x is less than or equal to xi minus 1, which is 1 minus f xi minus 1. And that's the end of that problem. And certainly because of time, it's the end of today's lecture. So thank you very much for being here. I hope you enjoyed it as much as I did.